Okay, so we're going to bring up one more system property, but let's just kind of summarize where we are, what we've found. If somebody comes in and gives you a differential equation, y triple dot plus some a y double dot plus by dot plus cy equals d times some input, okay, we would form, uh, let's just say, lambda cubed plus a lambda squared plus b lambda plus c equals 0. And we get the roots of this thing, okay? And in general, a set of roots can look something like, suppose we got a root that looked like go minus 7 plus, and you'd also get the conjugate 4i, all right? So we could take that and you'd plot minus 7, you put a 4i here, and you'd have, you see the minus 7? From the minus 7, you'd get tau equals 1/7. Settling time equals 4 over 7. Okay. From this height up here, you'd get omega d. So if you put a step input, you'll get some oscillation. That'll be 4 radians per second. Okay. So we have omega d. We have on here tau, settling time. This distance here, 7 squared plus 4 squared square root, have no idea what that is. Don't care. That'd be omega n. And if you check this angle in here, okay, the cosine of that angle, we would get damping. So we've got damping information. We've got natural frequency information. If we let, so these are all parameters that describe what's happening for this root, set of roots that we can't come out of this. There's going to be 3 roots that came out of a third order. But we could also then, we can get static gain. Where do we get that from? We let all the derivatives be 0, so we'd have cy equals dx. So you'd get static gain, cy equal dx. Bring that to the other side, you'd have y equals d over cx. D over c would be the static gain. All right. Now, we've talked about if we have the real part of the root, minus 7, if it's on this side of the imaginary axis, the system is stable. And that's the thing we want to talk about next. Turns out there's a bunch of equivalent definitions of stability. All right. So let's look towards that. So the following are equivalent definitions of system stability. They all, if you have one, you have the others. Okay. So one of the definitions of stability is that the initial condition response decays to 0 for any initial condition. So you can take something, with a spring, pull it back, it'll go ding, 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 ding. It always comes back to 0. All right. So if the initial condition response always decays to 0, it's stable. All right. Here's another definition. For every bounded input, the output is bounded. So for every bounded input you give, so it simply says you can have a crazy input, but we can come up with bounds for it. All right. So if that's your input, there's bounds. Okay. But here's an equivalent definition of stability. For every bounded input, the output is bounded. You can find bounds. So if you somehow could test every bounded input and check that you got bounded outputs for every one of these inputs, you would then know the system is stable. This is a little esoteric. And then here we have the one we've talked about. If the real portion of every eigenvalue, pole, root, is negative, you have a stable system. Okay? And then here's another one that's kind of fun. The coefficients of the characteristic polynomial for first or second order ordinary differential equations are either all positive or all negative. What am I saying? if you have 5y dot plus 6y equals 10x, that's guaranteed going to be positive. But if you put a minus sign in here, it's going to be unstable. Having said that, if I were to put a minus sign over here so they're both negative, then it would be stable again. For a second order, y double dot plus ay dot plus by, and this is based on the characteristic polynomial, so I'll just set it equal to 0. If these are both positive, it's stable. And this is a 1, it has to be positive too. But if you just have one of these be negative, so positive, negative, positive, this will be unstable. Now, if you write a third order differential equation, which I have here, okay, y triple dot plus ay double dot plus by dot plus cy equals the input. Okay, here's the deal. If these are all positive or these are all negative, it doesn't prove whether it's stable or not. You need them to be positive to have the chance of being stable, but it doesn't guarantee it. However, if you look at a third order or a fourth order or a fifth order where the signs are not all the same, so let's let this one be negative, you are guaranteed that that is an unstable system. It will blow up. Give it an input. For any input, it's going to go to the moon. All right? These, to have a chance at a stable system when it's higher order, they all have to be positive. Plus, 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 plus. This one doesn't matter. Or minus, 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 minus. If there's any sign change in here, you're going to the moon. And from a controls point of view, it tells you you got work to do. All right. So these are the various definitions of stability. And again, they're all the same. This condition implies these three conditions. This one implies these three, so on and so forth. And so next time we're going to start talking about a thing called convolution, which will set us up in afterwards. We'll then start Laplace. And convolution explains how systems actually respond to inputs. We'll start talking about that next time.